Okay, everyone. We're happy to have Ratul Mahanta again, and he will continue his discussions on uh, fermion fields today. Yes.
No, I'll first
Okay.
do the scalar field and then introduce the fermion. Okay,
Okay.
like,
Okay.
yeah. Okay, so last time we saw the Klein-Gordon field quantization for it, and we have mode expanded and got the commutator for the A and A dagger. And we have define the particle states and all excited states. So today I will start with discussing some normalizations on the state space. And so I will discuss only the one particle state. The reason I am discussing this normalization is partly maybe this relativistic normalization is useful when Taushik will be writing the S matrix element, or another reason it introduces an integral, Lorentz invariant integral. That's first of all beautiful and also will be useful for our discussion. So it's good to introduce these normalizations. So the one particle states we have defined as the creation operator acting on the vacuum. So the normalizations you can see that this is you can now use the commutator. We know this is nothing but, okay, so let's take P and some P prime. Okay, so this is yeah, so the first term will annihilate both way, because AP annihilates the vacuum. Also, if you take transpose conjugate, so you can see that A dagger from the right multiplications annihilates the conjugate of the vacuum. So what will contribute? The contribution will be these. And we have vacuum is always properly normalized. So this is our normalization for the one particle state so far defined. But this is not an Lorentz invariant normalization. To see this, let us use an identity operator. Identity operator is always Lorentz invariant because yeah, okay, so projectors and integral over that. So that's the definition, and it's Lorentz invariant because it's identity. Like it acts on a state and gives it back. Okay, so to check that this works, you can actually act identity on a momentum state, and immediately you will find it back. And we have just computed it. It is nothing but this, and if you do the K integral, it turns out that you will get the momentum state back. Okay, so this side it is Lorentz invariant, but the one particle states are not. And you can make it Lorentz invariant by considering this integral. So I will argue that this integral is Lorentz invariant, so it's a Lorentz invariant measure. So first I will state what it is. It is d4k delta, the usual delta, not the delta 3, and theta function. So this is Lorentz invariant. Okay, so I will check this equality. Before that, let me argue that this is a Lorentz invariant quantity. So under Lorentz transformations, d4k should transform as d4k times determinant of lambda. And we know that Lorentz transformations has the Jacobian is unity. And we also know that this leaves invariant. This is a invariant Lorentz scalar. This is the Lorentz Minkowski dot product. So it will also be unchanged. And theta k, it is a Heaviside theta function. So it states that for any functions, arguments, let me call it what, maybe say x, it is defined +1 whenever x is greater than 0, -1 whenever x is less than 0, and 0 whenever x equals to 0. So that's the definition I will be using. So it actually theta k naught picks the contribution whenever k naught is greater than 0. Now the integral d4k so the support of this integral is coming from delta function, and delta function imposes that k square equals to m square, which means k0 square equals to this. Yes. So you can see that the for momentum k is time-like. Because of the support of the delta function, it will force you to the momentum which are time-like. Time-like means k square greater than 0. Yes, because in our notation, in any for example, time-like vector in our notation is the time component. Okay, let me tell you for x. So x square is t square minus x square. It is greater than 0. So you can go to a Lorentz frame where only t survives. So it is nothing but t square. And for space like, you can go to a frame where t goes to 0. So it is actually negative. The spatial part dominates. So for time like vector, and it is the same definition goes for momenta. For time like momenta, because it is m squared and m squared is positive for us. It is one can show that Lorentz transformation does not alter the sign of K. It is a Lorentz invariant quantity. So I will not be proving it, but you can try to see that the Lorentz transformation that is connected to identity keeps the sign of K naught unchanged. Therefore, this since it has a delta function support, theta of K naught is a Lorentz invariant quantity. If K naught is greater than 0, it is always greater than 0. The sign does not alter. So this integral is Lorentz invariant. And we can now check that this really gives the expected result. So first of all, it is a delta function of some function of K. So a function of this function of K is K square minus M square. And suppose we want to look it as a function of K naught, because we will be doing first the dk0 integral. Why so? Because we want to check this. And if we do the dk0 k0 integral, then what is left is d3k. So that's what we'll be doing. So, and there is a formula for functions of delta functions. This is equals to delta f prime, sorry, it is okay. So let me tell other way. So for any delta f of x is some function, some variable. This is delta x minus xi and f prime x. Many people say that it is f prime of xi, but it is same because delta has only support at x equals to xi and the sum over I. So it means that, okay, xi's are the zeros of fi. So f of xi equals to 0. So xi are the zeros of that function. So that's how the delta function behave. And if you do this here, in our case, you will find that the function is this, and the zeros are at square root of plus minus square root of k square plus m square. Therefore, we will have contribution from this, and we have to also differentiate f prime k naught will be nothing but 2k naught. We have to take 2k naught following the formula for the delta, plus another 0 is at this, and again the derivative is that. So this quantity is the delta, how delta function behaves. Now I will multiply by theta and integrate over dk0. If you do that, you see that this term goes away because it has a support when k0 is minus, but theta k naught is non-zero. Okay, so let me do one thing. I am not using this definition of theta because, sorry, I will have a different definition of theta. It should be 1 and 0. Well, one can have a theta functions like that, and it is known that the derivatives of theta functions are delta function. But if we define that way, then the derivative will be twice of delta because of the gap -1 to +1. But I don't want that. So let me define it is 0 and it is half. So whenever it gets contribution only when x greater than 0 or x equals to 0. Whenever x is less than 0, theta functions go away. So that is the with this definition only this should work. This should match to the quantity we want. So that's our theta function. Sorry for the confusion. Now you can see that since it is negative, this will the second term will go away because it has a support when k naught is negative, but theta function only have contribution when it is positive. So what you get nothing but to k0, and k0 is positive. I am removing the mod, and since it has a if you do the delta function integral, it is nothing but 2 omega k, or it is nothing but twice of, and this is positive square root of that is what we defined as omega k. So you can see that this integral really goes to d3k divided by 2k. So this is the combination which is Lorentz invariant. It's clear from the this representation using the delta, and now the one particle state, one side it was Lorentz invariant. I will be writing it as I will just divide it by 2 omega k and we'll multiply. You can see that this is Lorentz invariant. So this projector should be it projects on a state, sum over state to some particular moment state. So this should be the correct normalization. And immediately you can define the relativistic normalized state as square root of 2k, 2 omega k vector. And if you okay, so and then this will look like these are the properly relativistically normalized states, and this is this quantity is E dagger k acting on vacuum. If you do the check the normalization, now you will get an 2 omega. Okay, so main point is I will be using that integral relation few times, and it is Lorentz invariant, this relation, and that's the idea I will be using. And this type of normalization, I don't know what normalization Taushik will be using, but for mathematics computations, but this has some manifest Lorentz invariance if you write in this form. So, okay. So Always it's up to you how you define the normalizations. So you can take your particle states as this, not as this. Okay. Okay, so maybe I will see if there is some question. No. Okay, so the reference is yes. So it's you can look at Peskin and Schroeder. My first lecture was mostly from the book Francesco. Now on, you can look at Peskin Schroeder chapter 2 and 3, and also I think you can look at the Ashok's lecture videos or lecture notes. Okay, so I will be now compute something else. So what other quantities you can compute? So that's the matrix elements. So various type of matrix element you can compute. So we have particle states, good, and what other some useful quantity you can compute, and so the things we will be computing are called matrix element of this kind. So vacuum expectation values of product of bunch of fields, a string of fields. So in principle, there can be. So these are the quantity. Although we need to define time ordering, I will be defining soon. With time ordered product will be useful for computing scattering matrix element. For now, we can compute it as some quantities we can compute in free theories. At the end of the lecture, I will be discussing that something why probably I will try to explain, or maybe Taushik can explain why it would be useful, but I can sketch. Yeah. So I want to, okay, let's give a name to this quantity. So this is delta plus okay. So let me also write the mode expansion of the field. We know that the mode expansion of the field is so that's the mode expansion, and from there you can see that in the product like this should contribute, this should not, from the left field, because A will annihilate the vacuum. On the other hand, from the right field, A dagger will annihilate the bra zero, but AK will not. You have seen from the um, from the property on the Kate, we have just seen the property on the bra space. So I think, yeah, so it's here, yeah. So uh, what will eventually, and of course for you have 2x, so you need to take 2k. And then only term that will be contributing is coming from AK acting on bra 0 and AK dagger. Okay, let me call it acting on Kate 0. And associated to this, there will be exponential. It would be minus I K1 X1. And for this, it would be this, but it is coming from the second field. So it is I K2 X2 with a plus because of this. And we know that this is delta function. It's not delta function, but only the delta function of that should contribute, we have just seen. So once you have a delta function, you can do one of the k integration. Let's do the k2 integration. It will nothing, it will become, it will be this, yeah. And since k1 equals to k2, this quantity will be minus I. So that's the integral you have to do to define, to compute delta plus. Now, from this representation of the matrix element delta plus, one can bring it to the Lorentz invariant form. So I will have another factor of 2 pi to the 2 pi just for convenience. Like it looks good because it's a 4-dimensional integral, and I will multiply by that factor. But we know that 1 by 2 omega k. Now on, I am not writing k1. I am defining it to be k because there is only one variable that is left after this k integration over k2. So this becomes theta k. That we have checked. So I can write it in terms of the Lorentz invariant quantities. Now you see that everything is Lorentz invariant. This is a Lorentz invariant dot product, and this product we have seen. The measure is fine. So also you can explicitly check this, but that's, I will not do it now. But if you compute for that like new points, the under the Lorentz transformations, you can change the integration variable accordingly to k equals to delta k tilde. If you want to compute the Lorentz transformed quantity, and you will get back to this. So that's the Lorentz invariance. So good. This is the Lorentz invariance. This quantity is Lorentz invariant. That's quite nice, and it will soon lead to causality. So later, let me first discuss causality in this theory, and then I can take some questions or yeah. So okay, so I am defining delta x1 x2, which is this. So this is a commutator. It will immediately give you so it can be written in terms of delta plus. The quantity we just computed, and we know that it has a Lorentz invariance. So idea is we want to check that outside light cone this quantity vanishes, and then we will try to interpret that this is what causality means. So outside light cone, it means that x1 minus x2 square is negative. The vector x1 minus x2 is space-like. So this is a space-like event between x1 minus x2 is a space-like quantity. So this is, which is the time component. Okay. So any space-like event under a Lorentz transformation equals to some negative number, right? So say it is some negative number. Given this, you can see that this quantity equals to a negative number. This is an hyperbola. So this is the light cone, and suppose it is the t-axis. This is the x, and of course there is multiple x-axis. Should be x1, x2, and say this is x0. The hyperbola is like that. Okay, so it's something like this. And Lorentz transformations is connected. So something which has a positive x1, x2. So basically under Lorentz transformation, x1 minus x2 can go to its negative value, minus of x1 minus x2 equals to x2 minus x1. Because for space-like events, Lorentz transformation can connect. On the other hand, for time-like events, it's not, because for time-like event, it is this. So there are two connected pieces, but whenever x0 is positive, Lorentz transformation stays within this surface. But whenever x0 is negative, it stays within this. So that's what the theta function thing I was discussing. But here for space-like events, they are connected. So, and we know that these quantities are Lorentz invariant. So we can write the first quantity maybe as, we can take it, okay, so in my notation, it was, although it's always function of the difference, in my old, the notation I defined, I should write it as with comma. Yeah, so I can, these quantities Lorentz invariant, in one of them you can perform the Lorentz invariant because these two are equal, and the other one you leave it as it is. But choosing a Lorentz transformation, you can exactly go to x1, x2 to x2 minus x1, and that's the combination it's depend on. You have seen that it depends on this combination. It's x1 minus x2, the difference that's matter. So basically you can make it equal to same as delta plus x2 minus x1 by choosing a Lorentz transformation. So this is one way to see that so same quantity and minus a quantity minus of the same. So this should go to 0 for space-like events. And another way you can see that since mm, this is the left hand side is Lorentz invariant, show the right hand side. Now I act Lorentz transformation on both of them. So this is equals to, so this quantity delta without the plus is a Lorentz invariant quantity, which is the vacuum expectation value of the commutator. Therefore, given a point x1 minus x2 less than 0, we can go to a Lorentz frame such that the time part go away. Only the spatial part remains. And you know that then delta becomes, so go to a Lorentz frame. Such that you can only for space-like event you can do that. And there this delta in that frame, it has a Lorentz invariant, so I can go to that frame. It becomes equal time commutator. And in our quantization rule, this is 0. So that was for phi and only phi and pi was non-zero. Otherwise, it was 0. If you remember, you can recall that that was the case, and that's how we have started quantizing. So that's there. So outside light cone. So this is the light cone. The cone inside, and outside light cone means the space-like events. So for space-like event, vacuum expectation value of commutator vanishes. It's the matrix element for so for any state like okay. So what does it mean for arbitrary say space like for which uh, not equals to 0. So this vanishes. So the commutator is 0. So it's a statement like for even earlier we had it for equal time commutator, but it now generalizes to like even for non-equal time events, but space-like events. So it means that these two operators cannot can have simultaneous eigenstate. So whenever events are outside light cone, for example, at an instantaneous distance, like when x1 0 equals to x2 0, the time is equal, or maybe so for that where you cannot connect by a causal ray. So this will be equal time, this will be the commutator which is vanishing. It means that they can have simultaneous eigenstate, and you can measure them independently. Like if it was non-zero, then measurement of one quantity should, so suppose between two operators, it is not zero, and then they don't have any simultaneous eigenstates. So it means that measurement of A affects the measurement of B. But since it is zero, so you can have a simultaneous eigenstate and they do not interfere. So that's the causality known as microcausality. We should be This should also guarantee between the observables, although we have defined for it for phi, but observable in the theory will be some functions of phi. So for them also it is guaranteed by this relation. So this is the basic commutator. It should guarantee the property that among observables the commutator outside light cone should vanish. So, and it means it's causality. So it's called microcausality. It's because there is a notion of macrocausality in classical mechanics that like nothing can travel more than the speed of with the not yeah so speed of light is the maximum speed. It cannot travel faster than that. So it's not what we are stating here, but it's the quantum mechanical version, so known as microcausality. So I should stop here and take questions. Yeah.
Hello, sir.
Yes, I.
Yeah, sir. Why we are interested in space? Like, I mean, why we do not go to the time? Like,
Yeah. So we are not like it vanishes only when it's space-like events. We are also interested in time-like, for which
but it should
it
be
is not
greater
zero.
than the speed of light.
Yeah, that's why it should vanish. That's what I have.
Yeah. So
Yeah,
it's like the
that's.
which particles created the different locations and they like annihilate each other. Yes.
I have not uh, defining it in terms of propagator.
Yeah.
But
Okay.
it is true that it is well, it is what I said, that it's the commutator outside light cone should vanish, because there should be a simultaneous eigenstate, otherwise the measurement should affect. Inside light cone, this quantity delta uh, without the plus is non-zero, and for time-like events.
Yeah. Okay. Thank you, sir.
Yeah.
Hello. Can you go to the previous page of this page number 7?
There is
Hello.
a interference, I think. So
Hello. Can you hear me?
yeah, I can hear you, but there is a in. Okay, now I think fine. Yeah.
Can you go to the page 7?
Yeah.
So how you
Uh,
decompose that argument of field into time and space part?
Sorry.
You write the phi x0 and x1 and phi x0 and x2, right? Means you
Yeah.
go to
Yeah.
so at first you write the field in particular space-time event, and then you decompose the argument of the field, and is by which you are leveling the field, the events into time and space part. Means
Well,
like
so
phi
whenever I
x0.
write, yeah, it's just a notation. So whenever I write this, you think of it as x0, x1, x. So that's a notation.
Okay, thank you.
Yeah. Because you can see that it's the 4 momentum. So k dot x will be like it has the time and also positions, and k is integrated over. K is always, because also k0 depends on the k vector, so you can integrate out. Finally, it would be function of time and spatial coordinates. Yeah. Any more question? Well, if you have a question, you can raise your hand, or I should proceed. Maybe I'll just introduce the time ordered product, and that's what will be appearing when you compute the S matrix element. And yes, so that's what. So those are okay. So I will now define time ordered product. Suppose you have a string of fields. So a time ordered product of them brings it to a particular permutations where I1, In is a permutation of the set of numbers, first n numbers, such that they are ordered in time. Okay, so let's talk about an example. It will be clear. So time ordered product of phi x1, phi x2 will be equals to phi x1, phi x2 whenever this, or it will be phi x2, phi x1 whenever the time of x2 is greater than the time of x1. So that's not the usual product. You have to arrange it in a way so that always which is in the future remains in the right, in the left side. Yeah, earlier probably I commented about something. Okay, I think there is a left right issue. Okay, so here it is yeah, so that's the left. So okay, so whenever anything in the future should sit in the left. Okay, so that's the time ordered product. You can also write it in a for 2 point product of two scalar fields. The time ordered product you can write using the theta function. So it means this will survive whenever x1 0 is greater than x2 0, and this is and in other case it is 0, this will survive. So this is you can write in a combined form. So in quantum field theory, what appears in the S matrix element, the scattering amplitude, are the correlators of so these are known as correlators. These are vacuum expectation values of time ordered product of fields. So that one can write as usually call it Green's function or correlator will be some finally function of x1 up to xn. So this is what these quantities, these endpoint correlators, people call endpoint correlators. That's what appears in the S matrix element. So we'll be dealing with it, but after a break. So we'll see that how it connects to delta plus for 2-point function. 2-point function means we'll be dealing with time ordered product of these two, how it relates with this. So that we will be discussing. Okay, so I should take a break for 10 minutes, but I am here to answer your questions. Yeah. If you have a question, you can ask. Can you explain how the fields are ordered in time again? So it's not usually ordered, but we are defining a time ordered product. Like we will order by hand that whenever the time of I mean the future time, the field with future time will be on the left hand side. Yeah, on the left hand side. Yes. Any more questions? Yeah, please raise your hand. I can unmute you. Okay, so the question is why the delta 3 is not Lorentz invariant. Yeah, so I have not directly proved that. Rather, I have argued that it should not, because from here, so this is not Lorentz invariant. Identity is, so this should not be. So first write something which is Lorentz invariant, and then whatever is left, the product should also be, so that identity becomes Lorentz invariant. So this give you a hint that the Lorentz invariant normalization should be this. So that's how I try to argue. Yeah, any more questions? Okay, if not, then we can really take a break for 5 more minutes, and then we can start again. Okay, I use delta x1 minus. Yes, finally it's true that I should have. Yes. So I have defined delta plus x1 comma x2, but the dependencies is coming from x1 minus x2, this thing. Of course, the sign will matter, so I should call it this, because that's the combination appears here. how we make measurements on these fields experimentally. Well, I have I talked about the vacuum expectation value of the commutator of fields, but in actually you have to think of observables, say Hamiltonian or momentum and others, which depends on phi. And the observables, so the yes, so the their commutator should vanish outside the light cone, and you can we are the use of field theory is like computing S matrix elements, but at least it is they are the time ordered product, and their correlator will be appearing. But the theory is causal. That's what I wanted to mean. So what you measure in experiment is particle scattering amplitude, and that's where these correlators will be appearing. And I just wanted to tell you that the theory does not violate causality. Yeah. Any other question? If not, I will then start the next part. So just ask if you have any question. Yes.
Yeah, I just want to connect my quantum mechanical knowledge to this way, that how this the time ordering of field coming from where, means dynamics of what, means Dyson series or something like that, means
Yeah, that's where it will come. So I think Toshiko will be dealing with interaction picture, and he will show that these are the quantities, the correlators, which are vacuum expectation values of time ordered product of fields that will appear there. Yeah, you're right.
and we can do mode expansion in interaction picture also, right? Means I do
In
that.
the whole canonical quantization that me and Taushik will be dealing with, it's the using the mode expansion. And then there is another way of quantizing thing, means at least getting the scattering amplitudes, rules for it. That's called path integral quantization. I think that would be dealt by Nabil and probably continued by Gonzalo. I don't know. Yeah. Okay, so I'll be starting the uh, next half. So as I discussed, the correlators, we should compute them. I will start with, and mostly I will discuss the 2-point correlator, which is time ordered product of two fields, and this I will be denoting as, okay. So here F stands for Feynman. And immediately you can see that it has the property x2, x1, because it is defined by with time ordering. So what it is this. And since it is already under the time ordering, it will pick up which field is should be on the right, which field should be on the left. So under the time ordering, permutation of fields does not matter. So even it is true for Green's function, the permutation of the coordinates like x1 up to xn should not matter because it is always under the time ordering. So it will automatically take care of because it doesn't matter what you write on the left and what you write on the right. Time ordering given x1 and x2, time ordering will pick what to put on the left. Okay, so let us try to compute this Feynman propagator. It's also called Feynman propagator, yeah. So or 2-point correlator. So this is nothing but vacuum expectation value of theta okay. So now it is maybe familiar to you. This is nothing but yeah, that's how we define delta plus by the vacuum expectation values of unordered field. So that would be so in integral representation, this is okay. I think we what we got. So for the correlator, yeah. So we got this formula. This will be using. Okay, so that's the formula you can use to compute the Feynman propagator. But I will now make a claim. That claim is this is some momentum space propagator and its Fourier transform. And where explicitly this is given by you have to integrate this by plugging delta tilde f, and then you have to take epsilon tends to 0 plus limit. So this should give you the quantity that I have just written here. Okay, so it is not very obvious that this will okay, so you will see the momentum space representation a lot, and that is called the free particle Klein-Gordon propagator, and it will be used by Taussig a lot, I suppose. And this quantity delta tilde, I will now try to integrate and motivate you that you will be getting the thetas multiplied with the quantities integrals written there. So again, I will be doing the K0 integral to do this, and I am particularly taking 1 by 2 pi out because finally we want to get a 1 by 2 pi cube. So if you do that, the K0 integral, it is okay. So you can see that this integral, the poles are like we'll be doing a contour integration, and in the complex K0 plane, the location of the poles are this. So it is minus k plus some I epsilon prime and plus omega k minus I epsilon prime. Okay, so first, if there is not the I epsilon, so you can see that K0 has poles at plus minus omega k. And since we are integrating over the real line, if the poles are here, we cannot do the integration. Then this is the Feynman's prescription that you shift them by some epsilon by hand. So usually the whenever m square appears, you have to shift it by m square minus I epsilon. So it is, there is another minus in front of m square. So it is always, so that's the Feynman prescription. So what it makes, it shifts with some, of course, you have to compute what is epsilon prime. It's because you have to take the square root. I am not doing that, but the idea is that it will shift the pole here. And on the other hand, it will shift the pole here. Now, none of the zeros of the none of the poles of the integrants lies on the real axis, and you can do the integral. Otherwise, if along the line of integration 1 by 0 is a problem, this we do not want. So okay, so this can be done using a contour integral. For example, whenever, okay, I should say it is this. So whenever x10 is greater than x20, this quantity minus I k0 x10 x20, suppose k0 is complex and it would be something r cos theta plus I sin theta. So we want to do it by contour integration. So I am claiming that this should be the contour. So that was that, and then we will be closing this way. And this contour would be at very large. So here k equals to, in the k0 plane, it is some r e to the power I theta. So we will be closing the contour, and the we'll do a contour integration, and the integration along the arc, like the semicircle, it will drop down, because you can see here at least the real part of it goes as it comes from the second term, so it's x10 minus x2 sine theta times r. And since we are taking the lower half plane and sine theta is negative there, so this quantity is 0, and this sits in the exponential. So exponential of some negative quantity and r tends to infinity limit, this contribution should drop. So you can actually think whenever x10 is greater than 0, you should close the contour that way, and you will take the residue contributions. And since the contour is closing the pole in the clockwise manner, so in the residue theorem we have to take a minus as well. So that's that minus, and it would be these 2 pi, and the residue is okay. So if you see here that if you see here that it is the pole is coming from k0 equals to, this pole is coming from omega k minus I epsilon prime. So the function should be evaluated at minus I omega k. I am not writing the I epsilon, because in epsilon tends to 0, it will go away. And this is there, and from this quantity, because it has 2 poles roughly. Okay, so this quantity goes as, it's not mod, I should say. Okay, let me say this way. This quantity has k0 minus omega k and k0 plus omega k. For computing residue at k0 omega k, this will be there. So it would be k0 plus omega k, and you will be replacing k0 by omega k. So what you get is minus I square is 1, 2 pi get cancels, e to the power minus I omega k x10 x20 divided by 2 omega k. Now probably you can identify that you have, whenever this happens, that x10 is in the future, then the x20 you have reproduced this term, because in that case this term is 0 because of the theta. So you have got, and this is 1. So you have got the expected result. So I am not repeating it for the other case, but for that you have to close the contour in the upper half plane, and you can probably do it as an exercise. Idea is that this claim works. So this should be the Feynman propagator in momentum space. Another thing I want to state here, that is the Feynman propagator also satisfy the Green's function. So what is typically a Green's function is, so we have a Klein-Gordon operator, which is a differential operator. A Green's function the solution to Klein-Gordon operator. So usually it is a function of 2 points x1 and x2, and say you are computing it at like del mu, I should write del mu, 1 mu is like this. So at the first position, and okay, so this is known as Green's function, which set for the operator, the Klein-Gordon operator. So we need to check that Feynman propagator. The claim is that the Feynman propagator is a, again, I am interchangeably writing is as a function of x1 minus x2 because that's the combination appear. I will, one can check that this is the I delta f is the Green's function, and that I will now be doing. It is, you can do it using the representation given here, because whenever the delta, the Laplacian will act, will act only the exponential because it has the position dependence. So this box operator will act on the, okay, let me write it. I and delta f is this 1 by 2 pi 4 d4k delta f tilde k. And this will act directly on that. And what it will give, it will, this operator acting on this will give you, okay, there is a I to track about, and there is also an I here. So let me do it. So it should be I square 1 by 2 pi to the power 4 integration d4k, and I am the another I come, it is because I am writing delta f k in terms of the Feynman propagator, so which is I divided by k square minus m square plus I epsilon. That I is already here, and you can, the box operator will make it ik square plus m square, and then that's there. So from there, you can see that d4k, and in the epsilon tends to 0 limit, the first quantity is minus k square plus m square, and the denominator is that, and this gives you -1 in epsilon tends to 0 limit, and this will compensate the minus here because I square will give another minus. Okay, so now you know that this is the representation of delta 4. Okay, so we have shown that the Green's function, the Feynman propagator is a Green's function of the Klein-Gordon operator. So that's another terminology people use. And now I will be since I have told you that what will be appearing is not 2-point function, actually many point functions. So yeah, I will take your question. Just give me 1 minute. So now I will tell you a theorem which is known as Wick's theorem, and then we'll probably switch to Dirac field. Okay, so yeah, so ask. Yeah. Yes, I think I have permitted. If you have a
So I epsilon give me the choice of contour, right? Means many possible choice of contour in the prescription of Feynman.
well, so you can have different sign with I epsilon. Then, like if you do not take minus I epsilon, if you take plus I epsilon, then you can you need to take even for x10 minus x20, you need to close the contour other way. But we have seen that only this prescription gives you the time ordered product, because we already know that time ordered product should be of this form. And now what prescription should reproduce them is the Feynman's prescription. So otherwise you can get say out of time ordered and other things you probably get. But here, since we will be interested in time ordered product, this specific prescription will lead to that. If you have other prescription, you do the integration with, you will see that you have to close the contour in other ways, and sometimes even both the poles will contribute, but none of them will reproduce these results, which is the from here you can identify that we have just checked that this claim works, that this equality works. Any other question? Okay, so I also don't see questions in chat, so maybe I should then proceed. Okay, so we are interested in time ordered product of say n fields. We have only computed the 2-point functions, but eventually for multi-field it will be just product of 2-point functions. So that I will now show. For example, say the Green's function, it would be nothing but so that's the property of free field. You can use this is a very nice property. So it's just a product of 2-point functions and sum over them. So on the other hand, this quantity is the time ordered product of 4 fields and its vacuum expectation value. Okay, so we will be stating a theorem which is called Wick's theorem. Before that, I need to define one thing which is called normal ordering. So I have phi of x, which is okay. I have invented a notation that instead of writing every time d3k by square root 2 pi cube 2 omega k, I'll write this box of k. So it means the integration measure. And you have ak. Okay, so we know that that was the Fourier decomposition for the field. And you have two parts. I will be denoting it by phi minus x and phi plus x. So what is phi minus x? Phi minus x is the part that contains the annihilator. And phi plus x is the part that contains the creator. Okay, so why I am introducing these notations? Because now I will be defining, you know that annihilator annihilates the vacuum. So I will define a normal ordered product. So it is not like we already implicitly used it for the Hamiltonian. So idea is move all the annihilators to the right and all the creators to the left. So that's understood. So I am just first giving you some example, and then I will, well, I have already stated what it is. So suppose you have a product of some operators like this. What you have to do, okay, you can define it for K prime also, but you have to do it this. So this product gives you, puts the annihilator on the right and the creator to the left, although it was not like that. So, for example, you have say phi 1, phi 2, a normal ordered product of them. Phi 1 is phi at x1 and phi at x2. And we know that each field, phi x1 and phi x2, has this creator and annihilators. Minus are the annihilators, and plus contains the creators. So it will be a product of, I can do it. So it has minus and then plus. So inside normal ordering, this is these are not dagger, these are the plus. Okay, so that's what I have defined. Now you see that all the operators are normal ordered because all the annihilators which are there are on the right hand side. Here there are no annihilators, but all the creators are on the left. So idea is even creators are on the left, the vacuum expectation value of that operator will be 0 because creator acting on the vacuum or annihilator acting on the vacuum, like it's the bra and kit, it makes it 0. So any normal ordered product we'll have a vacuum expectation value which is 0. And that's what we did for Hamiltonian. We found something, but what we prescribed was nothing but the normal order product of the original one. So like the old one. Okay, so let us apply the normal ordering. This is the one which is not ordered. So sorry, I will find it phi 1, phi 2 minus. This I have to switch. So I am writing it, say, on the red. So it is the definition of normal ordering. Rest of the terms are as it is. Yeah, immediately you see a version of Wick's theorem. So what it is? So this is, you see that normal order product of phi 1, phi 2 is the usual product. The first line was the usual product, which was phi 1, phi 2. And then you have omitted this term, you have added this term. So what you have to do, so if you have this, it is not the normal order product. You have to subtract a term. So that is this term here. And then you have to add this term. So that is the term there. But you can identify it as the commutator between phi minus, phi 2 plus. So this is a version of Wick theorem. I will explain more. So this is the usual product minus a commutator. But this commutator is nothing but a number times identity. And why so? I can prove it that way. So phi 1 minus phi 2 plus this commutator. If I use the definition of plus and minus, like it's written here. Yeah. So plus has a dagger k and with e to the power plus I k dot x. Similarly, minus has a k and this. So you can, it turns out that it is, you can check it. Okay, so what was my notation? My notation was, okay, k, not dk. So it is the integral over the k1 and k2. And you will find a commutator. So this contains the annihilator. So that's the one. And then you will get the creator and also the product of, like, exponential will give you to this. And this we know is nothing but the delta function. And you can integrate over, say, k2. Immediately you will get d3k. And I'm now writing back the, like, notation. It was by definition it was with a well, so we have this and also this. So this will square what was in the denominator, I k1 dot x1 minus x2. This is nothing but delta plus x1 x2. Okay, so this commutator is a number times identity operators, because it has an identity. So it's the operators. Commutator between the a dagger is not a number, it's a number times identity. Many times I'm not writing this identity, but it's there. So what we get, we get that this quantity is the delta plus. So this will lead to phi1, phi2 equals to normal ordered of phi1, phi2 plus delta plus x1, x2 times identity. So this, if you switch the side, you will get that. Yeah. Now what we are will be doing, we will be writing the simplest version of Wick's theorem. So time ordered product can be written in terms of normal ordered product and the correlators, 2-point function. So that we will be doing. So this is, we know that the time ordered product was by definition phi1, phi2, x2, 0, phi2, phi1. And we have seen that phi1, phi2 is normal ordered product of phi1, phi2 plus delta plus x1, x2 identity. If we plug it here, you will get theta x1 minus x2 plus theta, this time normal ordered product of phi1, phi2. And again, under normal ordering, n of phi1, phi2 equals to n of phi2, phi1. For fields for Feynman, there will be a minus, but you can check that. So I can pull this, but for this part, it will give you delta f x1, x2 times identity. And the sum of theta function, either of them contribute, either this or this. So it is 1 when this is 0, 0, 1. So the sum is 1. So what you get essentially is the time ordered product is normal ordered product of phi1, phi2 plus Feynman propagator times identity. So this is a version of Wick's theorem. I will state the general version. So define Wick contraction as suppose you have a set of fields, say under the normal ordering, phi1, phi2, phi3, phi4, and you write this notation, means these two fields should be omitted out. So phi1, phi4 left, and you have to replace the contracted ones by its propagator, a 2-point correlator. So that's the definition. You can define it for product of and if you contract two fields, it would be nothing but phi1 L minus 1. L will be omitted, then it would be start from L plus 1, then again phi m minus 1 and phi m plus 1 to phi n. So times the propagator between L and M. So that's the general definition of Wick contraction. The theorem states that the time ordered product is equal to the normal ordered product plus all possible ways of contracting pairs of fields within it. So I will explain it in an example only. So take this. What does the theorem says? It says that this is the normal ordered product and all possible ways of contracting it. So phi 1, phi 2, phi 3, phi 4. Say start contracting these two, means it's a normal ordered product between these two, and propagator will come out plus phi 1, phi 2, phi 3, phi 4. Contract these two, phi 1, phi 2, 3, 4. Contract these two. What else? Okay, 1, 2, 2, 3, 3, 4. Sorry, phi 1, phi 2, phi 3, phi 4. 1, 3. 1, 4. Okay, I don't, and then there are like, yeah, I think, am I missing something between, okay, I missed 2, 4. If I have a repeated, ignore them. And then there are phi 2, phi 3, phi 4, double contractions. Okay, so now you see that only the last quantities, these are the product of propagator. So this will lead to delta F x1, x2 and delta F x3, x4. The this will lead to, and others are also product of propagators. But if you take this term, this will give you phi 1, phi 2 normal ordered and a propagator of x3, x4. So this is the Wick's theorem, but if you put it inside a correlator, like the endpoint Green's function, endpoint correlator, whatever you say, what we want to compute, since normal ordered products will be vanishing because it will annihilate the vacuum, what will survive? Only the last 3 terms. And this will give you the product of correlators. The other 2 combination I have written earlier. So basically any endpoint function, you can try to do it with 3-point function. You will see that for 3-point function, any odd point function, the time ordered product, the vacuum expectation value of time ordered product of odd point functions vanishes. In this free scalar theory, only the even ones will survive, and they will always will be product of 2-point function. So in a sense, we are equipped with computing any endpoint function in this theory. So that's what where I would like to stop, and you can ask questions. Yeah.
Should I stop the recording?
Is there time for the Feynman, or all of that I should, maybe, yeah, I can start discussing it tomorrow, or I don't know.
Yeah, sure.
Okay. Although one lecture is not maybe sufficient, but yeah, okay.